Alright, so in class we saw how you can calculate the work done by a force, which is a variable force but in two dimensions. So we had the force was just I hat F sub x plus J hat F sub y, and we found out how you can calculate the work done by this force when an object moves from one point to another along a two-dimensional curve, which was specified by y as a function of x. So in this video, I'm just going to show you how you can calculate the work done by a three-dimensional force. So now we are going to have k hat fc, and in three dimensions, if a particle is moving along in a curve, this y as a function of x is really not the best way of representing the curve. It's much better to represent the curve as a parametric position vector, r function of some parameter. So the particle will be following a three-dimensional curve specified by this parametric position vector, and we're going to have a force which is three-dimensional, and we'll see how we can calculate the force. In other words, this is just a line integral of a vector field in three dimensions is what I'm going to show you. Alright, so our force is I hat fx plus j hat fy plus k hat fc, and these in general, the fx, f sub y and f sub z are the components of the force, and they can depend on x, y, and z. So they all depend on the position. All right. The particle is following some curve. Um, so let's say it's going from here all the way to here along this weird curve. And so this curve is specified by a parametric vector. So any point along the curve is given by this parametric position vector r, a function of s. And so what this means is that you can plug in different values of s, and you will get different points on the curve. So for example, the particle started out over here, and so the vector which gives you the starting position of the particle, the s that corresponds to that is s sub I, and let's say the particle ends up over here. Oops. The vector that gives you the ending point of the particle is this one, and the s that corresponds to that is s sub f. So between s sub I and s sub f, all the other intermediate values of s give you the position of the particle, the position vector of the particle at other points along the curve. Okay. Now, how do we calculate the work done by the force F as the particle moves from its starting position to its ending position? Well, the method of working is identical. Um, you consider an infinitesimally small displacement dr, find the work done over dr by using the simple formula for work, and then add up all of these infinitesimal amounts of work to find the total amount of work. Right? All right, so let's just think about this dr for a moment. So the position vector was r sub s, then the particle made a small displacement dr, and it moved over here. Now the new position vector is r, and s is changed by a tiny amount. Let's say it's changed by s plus ds, right? Okay, so s has changed by this infinitesimally small amount ds. So the new s is s plus ds, and as a result of that, r has changed to r of s plus ds, and the change in r is represented by this position vector, by this displacement vector dr. So dr is our infinitesimal displacement vector. Now how do I find dr? So for this we are going to use a result from differential calculus, which says that if the change in s, ds, is truly infinitesimal, then the change in r is going to be given by this equation. So it's the derivative of r with respect to the parameter s, and this derivative is evaluated at s, multiplied by the change in s ds. Okay, so this equation is approximately true when ds uh, is very small, and it's exactly true when ds tends to 0. So that's why it's important to consider a infinitesimally small ds, because for an infinitesimally small ds which is tending to 0, dr is exactly given by this equation. And by the way, this quantity dr is called a differential. Okay, all right. Now that is all that we need. So dr is equal to the derivative of r with respect to s multiplied by ds. All right. So now we can go ahead and calculate the work done. So let's calculate the work done over dr. It's just going to be f dot dr, right? Let's plug in the dr that we just got. So that is going to be um, f, okay, I'll just write that over here. So the work done over dr is going to be f dot dr, and so that's going to be um, f dot dr ds. Remember, the dr ds is a vector evaluated at s multiplied by ds. Okay, and strictly speaking, this f is whatever the value of the force was at the starting position. We are assuming that the value of the force did not change very much. So let's say the f was something like that. The direction of the force was that, and that is the f at s, right? We are assuming that it's going to be the same f over our infinitesimally small displacement dr. So we are assuming that dr is so small that f doesn't change over it, right? So that's how we did f dot dr, force times displacement, dot product of force and displacement. So strictly speaking, I should just write write this f as f at the parameter s. So that is the work done over an infinitesimal displacement. And so the total amount of work done in going from A to B will just be the integral of all of these, or integral of all of these dw's, which basically means just add up all these dw's. And so that is going to be the integral of this whole thing. So f evaluated at s dot dr ds evaluated at s ds. So the integrand is just a big function of s, and this has to be, so the whole thing is being integrated with respect to s, right? So the starting position A corresponds to s equals si, and the ending position B corresponds to s equals sf. So that's it. That's all there is to it. All right, so let's look at a actual example. So I'm just picking a random example from a textbook. Let's see. So we are given a force F. So this is an example. We are given a force F which is this complicated force 8x square y z I hat plus 5z j hat minus 4xy k hat. Okay, so this is the x component of the force F sub x, this is the y component of the force F sub y, and this is the z component of the force F sub z. So you can see that both F sub x, F sub y, and F sub z in this case depend on x, y, and z, right? So this is our force in vector field force. Okay, now we are told that a particle under the influence of this force is following the curve moves along the curve which is given by r of t is equal to uh, I hat t. So t is the parameter, it's a parametric position vector, plus j hat t square plus k hat k hat t cubed. Okay, so if you compare this, as we've done in chapter 1, if you compare this with the generic position vector r, you can see that this is, it's, so the generic position vector is I hat x plus j hat y plus k hat z. So you can clearly see how the x, y, and z coordinates of the particle depend on the parameter t. So you can see from here, by comparing these two, you can see that x is equal to t, y coordinate of the particle is equal to t square, and z coordinate of the particle is equal to t cubed. All right. Okay. So we have r, right? And we have to find, and we are told that we're also given that um, the particle moves from t equals uh, 0 to t equals 1. That's also given in the problem. So the initial position of the particle is the one for which t is equal to 0, and the final position of the particle is the one for which t is equal to 1, is the vector r for which t is equal to 1. And all the intermediate values of t between 0 and 1 give you the intermediate positions of the particle. Alright, so we have to calculate the work done by the force as the particle moves along this curve, right? Okay, so all we are going to do is just plug into this equation. We are going to figure out each part of this. So the work done is given by the line integral um, t initial to t final. I'm just writing this again with respect to with t instead of s. F evaluated at t dot, there should be a vector sign here. F evaluated at vector sign here as well. F evaluated at t dot um, dr ds, I mean dr dt, also evaluated at t. So this dot product. So this dot product will be a scalar, and then you just integrate this with respect to t, and you should get the answer. So what is f evaluated at t going to be? So all you have to do is just plug in the uh, t for plug in the t, express x, y, and z in terms of t as we did right here. Just plug these into um, the expression for the force. So f of t would be um, 8 x square y z is what we have, right? So it's going to be 8 t square, y is t square, and z is t cubed, I hat. Then the next term is 5z j hat, so plus 5z, z is t cubed, j hat. And the third term is minus 4xy k hat. So minus 4, x is t, y is t square, k hat. Alright, so this gives you 8 t to the power of 7 I hat plus 5 t cubed j hat minus 4 t cubed k hat. Okay, if I did that correctly, I think that's correct. Okay, so that's f evaluated at t. Let's find dr dt. There's nothing new about that. It's just we've done this thing in chapter 1. So you differentiate, it's just the tangent vector of r with respect to t. So you just differentiate this with respect to t, and then dr dt will be I hat plus 2tj hat plus 3t square k hat. Alright, and then what we have to do is take a dot product of these two. So that would be 8t to the power of 7. So I'm basically multiplying the x components, multiplying the y components, multiplying the z components. Then plus, yes, plus 10 t to the power of 4, and then you get minus 12 t to the power of 5. Alright, so we found that. So we have figured out this whole thing, and then we just need to integrate this with respect to t. So the final answer will be the integral of this quantity, 8t to the power of 7 plus 10t to the power of 4 minus 12t to the power of 5 with respect to the parameter t from the starting value of t, which is 0, to the ending value of t, which is 1. And I'll just let you do this integral on your own. And if you work it out, and assuming I did all this algebra correctly, the final answer should be 1. And that is how you integrate a vector field in 3 dimensions. So the concept is the same, but it's more convenient to express the path as a parametric position vector rather than a simple curve y as a function of x, which is what we did in class.